Oh. All right, looks like it just rolled over to noon. So welcome back, everyone. I trust you also had a relaxing weekend. I visited with friends and family, so it was good. Let's see. So my main announcement is I have asked for 3 new graders. Whether we'll get all 3 of them remains to be seen. Again, that one guy is excellent. He's faster than I am. So as far as I know, that's in the pipeline. I haven't heard anything back from the staff member in charge of doing that. I guess she's having, it's not as easy working all that out from home, but I did send the email. So hopefully, at least by the time we've taken the 3rd exam, hopefully maybe they'll even clean up the grading on the 2nd exam and complete that one in a reasonable time frame. And complete, I mean the 3rd exam in a reasonable time frame. Good. So what else? I think that's about it. Looks like I'm already recording. Today we're going to start chapter 23. And as you'll see on the syllabus, that material will not be on exam number 3. It'll be in exam number 4. So the syllabus always says exactly what's going to be on every exam. But that being said, the material in chapter 23, which is, by the way, going to be our last traditional organic chemistry chapter, but the material is nothing more than combinations of things we've already seen. I think it's at the point that I'm not going to be able to surprise you with something completely new. So at least that's something I'm going to try my very best to convince you guys of by the end of class today. So, but again, please register your attendance. And in particular, when it comes to the Aldol condensation or all of the other carbonyl condensation reactions we're going to be looking at in this chapter, that would include the Claisen condensation and various kind of mixed condensation reactions, which we'll probably start to cover on Friday, is my guess. But what those 2 things have in common is 2 ideas that we've covered in previous chapters. And so I would say in order to learn what you need to know from chapter 23, there's 2 ideas that you have to have down absolutely rock solid. And one of those ideas is that carbonyl groups are electrophilic. We found this out in chapters 19 and 21 largely. Isn't Friday a read? It could very well be. That does ring a bell, actually. Oh, wait, is that the, whatchamacallit? Let's see, so 31, it's like the 2nd. It's not the 9th. Yeah, I think at least one of those Fridays is a reading day. So, well, if there's a reading day, then woohoo, we have no class. Good, but be that as it may. So carbonyl groups, as we've said, are electrophilic. And so what that means is we expect them to undergo nucleophilic attack when treated with some nucleophilic species, give or take whether we protonate the oxygen first. We would if we're in acidic medium so that we don't generate any intermediates that are strongly alkaline. If we're in alkaline medium already, then not so much, just bombs away and our nucleophile will attack. The reason for this, which you also need to be very clear on, the reason that this carbon atom is so electrophilic is twofold. You could understand it as being because you've got this strongly electronegative oxygen atom directly attached. And so by the inductive effect, the oxygen atom is winning that tug of war, so to speak, on the electrons in the carbon-oxygen bond. And so that puts a partial plus charge in carbon. That's one thing. Another perfectly valid way of looking at it is due to resonance. All carbonyl groups, regardless of where they appear, are resonance stabilized species. And there is a minor but still important contributor to the overall structure, which has a plus charge in carbon, a single carbon-oxygen bond, and a minus charge in oxygen. So certainly the majority of the structure is much better described, or I should say the structure is much better described by the other resonance form, but there is that component to the overall molecular orbital picture. And that also puts a plus charge in carbon. Both of those statements are true. And both of them explain why carbonyl carbons are such good electrophiles. So we got used, I think, in chapters 19 and 21 to seeing nucleophiles attack that electrophilic carbonyl carbon. I've just copied that over here for reasons that we'll get to. So that's one thing. That's one idea that we need to have down absolutely stone cold in order to be able to understand chapter 23. The second thing is that enolates are nucleophilic species. And we covered that idea in chapter 22, where we saw that you can take an enolate and treat it. Also, you can take an enol, by the way. Enols are also nucleophilic. And they're the way enolates would appear in neutral to acidic solution. But certainly in alkaline solution, these enolates can act as nucleophiles and react with any of a variety of electrophiles. The main ones we covered there were halogens, such as Cl2, well, halogens Cl2, Br2, and I2, in which your electrophile is essentially Br plus or I plus, etc. That the enolate will reform the carbon-oxygen double bond, go to the keto form, and pick up either I plus or Br plus or Cl plus from I2, Br2, or Cl2 respectively, and break that weak halogen-halogen bond. Or this electrophile could just as easily be an alkyl halide or tosylate, preferably primary, in which case this is nothing other than an SN2 reaction, which we discussed in chapter 11 last term, that we reform the carbonyl carbon-oxygen double bond, we break the carbon-carbon pi bond, and form a new bond to this electrophilic species whatsoever it might happen to be. And in order to learn what you need to know in chapter 23, all you need to do is take these two ideas and put them together. And here's something I tried in the previous class. I'm not sure this is going to work out perfectly, but what I'm trying to show you is what it means to combine those two ideas. Trying to get rid of the, oh, I know what my problem is. Trying to get rid of, well, my problems are several, but don't get me started. What I'm trying to do is visually put together those two ideas. Oh, well, I know what I can do without, yeah, there we go. Without having it look like double vision. So that's it. Right there, that diagram there is chapter 23 for you. It's observing that carbonyl groups are electrophilic and will be subject to attack by nucleophiles. And by the way, enolates are good nucleophiles. And all that's going on in chapter 23 is nucleophiles attacking the electrophilic carbonyl carbon of one carbonyl compound, except the nucleophile just so happens to be an enolate. That's it. That's all there is to chapter 23. If you understand those two ideas, then you have a more than adequate background to handle whatever we cover in chapter 23. And with that, as I said, that's going to be our last, what you might call traditional organic chemistry chapter. We'll have some chapters on biochemistry. We will have at least one chapter on polymers. And in those chapters, I think you will find that I am utterly unable to surprise you, that there's not going to be a single thing that's brand new in that chapter that we've never seen anything like it before. And then, of course, we also need to cover our last spectroscopy topic, which is proton NMR spectroscopy. And as I said, I'm confident, at least I think if you keep an open mind, you'll see why I postponed that topic. My feeling is the other types of spectroscopy are more than enough for one exam, for 1 hour exam. That's just my opinion, because proton NMR has significant complications added to it that are just not an issue in carbon-13 NMR. So you'll see when we get there, I think. Certainly there's a lot in common. They're both still nuclear magnetic resonance. There's a lot in common between those two methods, but proton has some extra tricky bits in it. So it's good to put it off as long as we can. My feeling with doing it afterwards like this is that this way it's also closer to the final exam. So that's not bad. You get to do some review of spectroscopy. You get to try your hand at combination spectroscopy problems. Because one of the things I've said is, Can you know what a compound is from looking at the IR spectrum? Absolutely not. No way. From looking at the mass spectrum? Absolutely not. Can you know what a compound is by looking just at the carbon NMR spectrum? Probably not, but you'd do better than with either of the other two methods. But if we were to be given a proton NMR, a carbon NMR, and an IR and a mass spectrum, then we can figure out what the structure of the product is. That's then enough information. So that's what we mean by a combination spectroscopy problem. And then you'll be able to finish your chapter 13 owls and all that great stuff. Okay, so that's basically it for the chapter, is bringing together those two ideas. Questions so far? Sorry for the lack of cat content. They both abandoned me. Maybe they're still mad at me for leaving them. And so I closed the door. But, oh, excuse me, sorry. Good, so an example of an Aldol reaction. As an example, I'm going to give the one in the book, not because there's anything special about it, but first of all, because it's a particularly simple one. Second of all, because I think there might be a couple of structure mistakes. I mentioned that here in your class notes. I think they forgot a hydrogen or something. I think they drew a letter C for a carbon atom that they would have better left as line angle, because the way they drew it, it looks like carbon is only 6 electrons around it. So as I recall, that's the mistake there. But in a typical Aldol reaction, one could take acetaldehyde. So here's a compound that has that all-important electrophilic carbonyl carbon, and also has at least one of those all-important alpha protons. So the idea is that you can deprotonate alpha to carbonyl on one acetaldehyde molecule and use that enolate to attack a second acetaldehyde molecule. And so after proton transfers, you would get, at least initially, you would get an adduct that looks like this. And I've drawn the new carbon-carbon bond that we formed in blue. That leaves otherwise two carbon pieces. Here's one of them, or I'm sorry, here's one of them, and here's the other. And both of those 2 carbon pieces will come from separate molecules of acetaldehyde. And so this would be what you could consider your initial Aldol adduct. We're going to find in practice, and this is one of those uncomfortable things, I can't make it completely black and white, otherwise I'd be lying to you. And I try to keep lying to a minimum, as we all do. But I can't give you a 100 or 0 type thing on this. But in fact, what we find experimentally is probably 90 to 95% of the time, these types of Aldol adducts undergo dehydration to form a new carbon-carbon double bond with loss of water. And I would say in probably 75 or 80% of the cases, if not more, that's a conservative estimate, what we find is isolating compounds like this is absolutely impossible. They're just too unstable, and even just under the reaction conditions needed to do the condensation reaction, the dehydration will occur and we can't even stop it. So that's also pretty common. We'll touch on that at the end of lecture today and probably bring up that point, let me get this right now, on Monday, a week from today, assuming that Friday is a reading day. Good. So that's what the initial adduct looks like. I had written out the mechanism before I remembered that I actually already have put it in the class notes. So the mechanism is, for us at this point, same old, same old. We learned in chapter 22 that you can deprotonate alpha to a carbonyl group, that such protons are slightly acidic, and we could use whatever choice of base. Here, of course, it doesn't matter whether we use a kinetic or a thermodynamic base. There's only one set of acidic protons on the methyl group. Of course, the aldehyde proton is not acidic at all. That's important to know. There is no base in the world strong enough to pull off an aldehyde carbon, largely because you would have a hard time putting a minus charge on that carbonyl carbon. It's just not something that you can do practically, but take however strong a base you like. make it as arbitrarily strong as you like, you will not be able to deprotonate an aldehyde proton. You can, with a significantly weaker base, though, deprotonate in the alpha position. And sure, hydroxide or an alkoxide group will not deprotonate that immediately and quantitatively, like LDA will, or one of those super strong bases, but it will still make enough of this enolate, a large enough concentration of the enolate, that the enolate will then be able to find another acid-aldehyde molecule. As you see over here, I've colored it in blue, and you will get, at first, this species here, which is an oxyanion. We're completely comfortable with species like that in alkaline medium, no problem whatsoever. And so, of course, this species can pick up a proton from water, not because it's always water, but because I look at what I'm given, and that's the most acidic species I see. Water is more acidic than ethanol, 5 to 10 times more acidic. I wouldn't say overwhelmingly so, but still, compared to alcohols, water is in general more acidic. Of course, unless you're talking about phenol, right? Remember, phenol is special. Phenol is not an ordinary alcohol like ethanol or methanol. But ordinary, as we call them, aliphatic alcohols that have alkyl groups as opposed to benzene rings, those are weaker acids than water, not by a tremendous amount, but they are weaker acids. And so we use a water molecule to put the proton in the oxygen, and we get this initial adduct. And as I said, in general, it's at least very easy, even if it's not unavoidable, it's at least very easy to dehydrate. And that's going to turn out to be an E1CB mechanism under alkaline conditions, which is something we covered in chapter 11. You might want to review that if you've forgotten about the E1CB mechanism. And so that's going to result in loss of water and formation of a carbon-carbon double bond conjugated to the carbonyl group. So we'll get to that later. We will at least be able to touch on that by the end of class today. And it's something I think will then be worth starting with again on Monday, because it's the kind of thing that I've observed needs some explanation, and I think it's not going to do us any harm to mention something like that twice. At least I have yet to have any casualties from mentioning a topic like that twice in 22 years of teaching. So I think you're pretty safe. Good. Anyway, once you do that, your initial aldol adduct looks like this. And again, here's one 2-carbon piece that comes from acetaldehyde, and here is the other. So this is a typical aldol condensation reaction. It takes 2 molecules of an aldehyde or ketone and combines them into one. And again, any aldehyde or ketone can undergo this type of reaction as long as it's enolizable, as long as there's at least one alpha proton, then you can get a reaction like this. And the product's generally pretty easy to predict. You will certainly always at first get an adduct of this type. I guess you could call that a beta hydroxy ketone or aldehyde. And then it's, as I said, quite common. I can't say 100%, but probably at least 90 to 95%, if not more. It's very common for these initial aldol adducts to dehydrate. But we'll get to that. By the time we end today, you'll have some information on how to know pretty much for sure that that's going to happen. And it usually will, but there's going to be some things that add a driving force to that dehydration. Good, I think I've said enough about that. Any questions on this mechanism of the aldol condensation of 2 acetaldehyde molecules? Let's see. So I did it again. I'm just that good when it comes to being a teacher. But seriously, I shouldn't be sarcastic. It's hard to avoid it though, isn't it? Before we get into any more details about the aldol condensation, and by the way, once you do understand the aldol condensation, all of the reactions in this chapter are real similar. There's sort of mixed aldol reactions that use 2 different ketone or aldehyde starting materials. I'm sure we'll do an example of that next time. Those are the most effective if we make one of our aldol partners have no enolizable protons. So this way you know what you're going to get the enolate of. So let's say you use 2 different carbonyl compounds, only one of which has enolizable protons, protons that are alpha to the carbonyl. The other one cannot form an enolate. Well, now you know which enolate you're going to make. I think in general, you'll find the one that you can't form the enolate is also, by virtue of that, a better nucleophile. So it's generally fairly straightforward to get a pretty clean reaction from that. And then when we get to Claisen condensations, those are nothing more than Aldol reactions with esters, period, full stop. And we'll find because we're starting with esters, actually the mechanism is simpler. It's a more straightforward, it takes fewer steps, fewer proton transfers. Good, but before we get into any of that, I want to make sure that we're clear on the difference between an alpha substitution, which we covered in chapter 22 just now, and an Aldol reaction, how you can tell the difference between them, apart from the obvious structural ones in the product. One thing that you'll notice about the reactions of the type we talked about in chapter 22, your alpha substitution reactions, is that you need an entire equivalent, an entire mole equivalent of base, because we need, whether instantaneously or over time, we need to convert all of our carbonyl compound to the enolate in order to get a reaction. And here I've chosen to use sodium methoxide, so I've chosen to use a thermodynamic base. I could just as easily have used LDA or something like that, and of course, with a starting material like cyclohexanone, it doesn't matter which you use. There's only one possible enolate because the compound is symmetrical. In any event, we need to form the enolate in order to be able to react it with our electrophile. And I'm just using methyl iodide to keep things simple. Question I often get about methyl iodide is, would it be wrong to put methyl bromide or methyl chloride? No, of course not. Those would do the same type of thing. But in real life, we prefer to use methyl iodide merely because it's a liquid at room temperature, whereas methyl bromide and methyl chloride are gases at room temperature. It's just a pain. You got to get a gas cylinder. You got to set it up so it doesn't fall over and explode like a torpedo. You got to get a cold bath so that you can condense the stuff out. It's a big pain to deal with gaseous starting materials. It can be done. And I've unfortunately enjoyed doing that more than several times. But if you can avoid that by using something that's a liquid at room temperature, you can measure in a syringe or a graduated cylinder, certainly you will choose that just because it's much more convenient. But from that, you would get formation of the substitution product. We've substituted one of those alpha protons for the methyl group in our methyl iodide. And so, but again, we do need an entire mole equivalent of that base because you need to convert all of the starting ketone or aldehyde eventually to the enolate. Whether you do it all at once with a strong base like LDA or harpoon base, you remember that one, then that's fine. But even if you used a thermodynamic base like an alkoxide or hydroxide, you need at least a full mole equivalent in order to get the job done. Meanwhile, with an aldol condensation reaction like this one, all you need is a catalytic amount of base. And you can tell that, by the way, when you look at the mechanism, because this reaction is only base catalyzed. There's no base consumed by the reaction. And you can see that right over here. Here's my hydroxide base. I'm pulling off my proton over here. So I'm taking a proton, so I now owe you one proton. You get our addition, that's fine. And then after the addition, I'm paying you your proton back. And so we're even now. So you see bases being neither generated nor consumed in an overall sense or in a net sense. Here I'm converting a hydroxide to a water molecule, but over here I'm taking the water molecule and making the hydroxide out of it. So you only need a catalytic amount of base in an aldol condensation. Often more than that will be used, in fact, but you only need a catalytic amount in order to get the reaction to go forward. Good, and that's what I'm trying to show here. And we'll go on to the dehydration in just a second, but apart from the dehydration, are there any questions on this idea? Quiet group again. We need to keep up some energy, guys. There's still quite a bit of semester left. So pump it up. Anyway, but if there's no questions, that's fine. I'm sure not going to hold that against you. Now, again, this initial adduct is probably pretty unstable. In this case, I think there'd be a significant driving force, and this might, in fact, be a time when you'd be hard-pressed even to isolate this beta-hydroxy ketone. Certainly, if you either heated the reaction mixture or you acidified in order to get rid of whatever base is there, certainly then you would dehydrate. And we'll go over what that mechanism looks like in just a moment. Because you will, in any event, again, get a carbon-carbon double bond that's conjugated to the carbonyl, so that's a driving force. In this particular case, on top of that, the resulting alkene is tetrasubstituted. That's as stable as you can get if you're an alkene. So this would be a case where the loss of water by an E1CB mechanism, just when we heat it even, and sometimes by heat, it's enough just to bring it up to room temperature. You don't even necessarily have to cook the snot out of it. But in cases like that, it's quite common that the dehydration will be either inevitable, in the sense you can't even prevent it from happening, or if not quite inevitable, at least very, very easy to effect cleanly. And in fact, compounds of this type are generally quite unstable because they dehydrate so easily. So in this case, if we lost a water molecule, we would get a species that looks like this, with a nice stable tetrasubstituted carbon-carbon double bond, which on top of that is conjugated to the carbonyl. So the driving force to lose water is very strong in most of these cases. And again, I can't say 100% of the time, but really 95% of the time is a conservative estimate. In general, in these cases, it's almost always the case, can't say always, but almost always, that if you heat the reaction, and sometimes heating, sometimes even warming it to room temperature is enough, you will lose water. And again, you'll be able to pick up cues from OWL or exam questions, especially if it's a mechanism problem. You've had, what, 2 of my exams already, not including if you had any last term. And not also even to mention that I have old exams posted on eCampus, but you already know that it's very typical for me, if I ask you to do a mechanism problem, to show you what product to aim for. The only time I wouldn't do that is if, in my view, it's unambiguous what the product would have to be. But I think if you look at past exams, you'll convince yourself that's the case. You know me, I don't like teaching to exams. But I recognize I've had to change my behavior a little bit. I recognize that sometimes I have to. You know, it's just kind of expected of me. So I'm at least trying to meet you halfway in regards to that, or in regard to that. Good. So this is just about distinguishing when you have an alpha substitution versus an aldol condensation, how you can tell which you're going to get based on looking at the reagents. Of course, having that separate electrophile there that's an alkyl halide is a dead giveaway for an alpha substitution as well. Good. So let's look at another example of an aldol condensation and touch on this topic of dehydration. So this reaction here, I've used the same one with cyclohexanone. This one here, I'm going to leave it up to you to work out the mechanism of that reaction with at least a catalytic amount of base, sodium methoxide and methanol. So I'll leave that to you. That would not be wasted time. And it wouldn't be, that would not even hurt your studying for the exam, because it's again involving deprotonation at the alpha carbon. So it's closely related to chapter 22, even though I'm not planning on expressly going for aldol reactions for exam 3. But see if you can work out that mechanism. That will not be wasted time. And as always, if you work on that and you're not sure if you've done it right and you want to show me, please don't hesitate. That's what I'm here for. But once we have this adduct, what does the loss of water look like? Well, over here, you've got a typical example of a dehydration that occurs, and we'll find that this is going to go, as I set up here in the class notes, by an E1CB mechanism. So if you've forgotten about those, please do review those in chapter 11. You need to know that in order to understand this mechanism. But an E1CB mechanism is essentially defined as having two steps. In the first step, we deprotonate to give a carbanion. That's going to be fast kinetically. All proton transfers are always very fast, and that I can give you 100% on. Any kind of proton transfer, acid-base reaction, those are always, without exception, exceedingly fast compared to any other kind of step. So we'll pull off that proton and you'll get an enolate. And once again, just as with any other enolate, if you wanted to draw the other resonance form that shows the minus charge in carbon and the carbon-oxygen pi bond still intact, you can certainly do that. It's absolutely acceptable, 100% acceptable. So that's our general rule for reactions that have any resonance stabilized intermediate along the way. And generally, you don't have to show all the resonance forms if it doesn't specifically ask you to. But when you have a resonance stabilized intermediate, which again is not that rare, in general, you can use whichever resonance form you like, and you should be able to find a correct way to draw the mechanism. Here I put the minus charge in oxygen, just because I kind of felt like it, but that's why we call this an E1CB reaction. The first step is a deprotonation. In an E1 reaction, the first step is loss of a leaving group, making a carbocation. So the E1CB reaction turns that on its head. So the first step is making a carbanion by loss of a proton, and then the rate determining step is loss of the leaving group. That's going to be slow in comparison. And so under alkaline conditions here, we're losing hydroxide as a leaving group. Hydroxide, of course, is a really bad leaving group. But in alkaline solution, it's good enough, especially when you wind up making a conjugated carbon-carbon double bond as a result. So that's a very strong driving force. So even though hydroxide is not a good leaving group, with those things stacking the deck, it's good enough that we're in alkaline solution and that we get a conjugated carbon-carbon double bond. If both of those things if either or both of those things were not true, I'm not so sure this reaction would go quite so readily. So I also said here, this is a nice summary. Look for the possibility of an Aldol reaction if you see a conjugated enone or enal as the product. Probably you're looking at some kind of Claisen condensation, or some kind of carbonyl substitution, especially in Aldol condensation. Claisens we'll get to later on. Here's another example of one. See if you can figure out the mechanism of this reaction. I have this in your class notes. In fact, I already have it over here. Maybe I'll give you even a few minutes to work on that. And if we should have even a little bit more time, well, then we can look at an example of a mixed Aldol reaction. That one's a crazy one, but we'll see if you can figure that one out. I'll make up a less complicated example than the one in the class notes, an example of a mixed Aldol reaction. But yes, see if you can figure out, first of all, the reaction of acetophenone with itself to make that, that beta hydroxy ketone. And this now is a case, I think it'll be utterly impossible to stop that from dehydrating. Because here you get not only a double bond that's tri-substituted, which is pretty stable, and conjugated to the carbonyl, but it also is conjugated to a benzene ring. And that's something that I want to give you to look for. If you wind up with an extended conjugated system involving not only the new carbon-carbon pi bond and a carbonyl group, but also at least one benzene ring, that for sure is going to be a case where you cannot even isolate that initial adduct. Even if you keep it cold, I think that will still undergo dehydration. So see if you can come up with that mechanism and convince yourselves as to why that is. While you work on that, maybe I'll set up a mixed Aldol reaction over here. But I'll give you, I don't know, 5 minutes or something to work on that. And then we'll go over it. Default, good. So what would be a good example? What about And then if you finish that one in our board, see if you can handle this entire aldol condensation followed by dehydration sequence. And I'll go over both of those in 3 or 4 minutes. If you'll excuse me for one moment, I've received a text. Back in 1 moment. Yes, Friday, whatever that day is, April 2nd, I think. Yes, Friday, April 2nd is a reading day, confirmed. So this is our only class this week. I'm actually glad about that. Let's do it that way. Let's take the exam, get it over with, so you can enjoy your weekend. It worked out pretty well. Okay. So the reaction of acetophenone with itself to, first of all, form an aldol adduct. You could say that adduct is a dimer if you want, since we're taking 2 molecules of the same. Starts with deprotonating at the alpha position using whatever is the base that we're given. And here our solvent, we're using a water ethanol solvent mixture. We're adding a little ethanol just to make sure that everything gets dissolved. Water is, of course, a little bit more acidic than ethanol. When I say a little, probably 5 to 10 times as acidic. So we'll remember to use water as our proton source, hydroxide ion as our base. And one acetophenone molecule is our nucleophile and another one is our electrophile. So once we've deprotonated and formed our enolate, all we need to do is invoke the enolate attacking a second neutral molecule of acetophenone. Of course, it wouldn't be able to attack another enolate ion, right? The enolate ion already is a minus charge. It's not going to undergo nucleophilic attack. So it will find a non-deprotonated, if you will, acetophenone molecule to attack. You'll get this tetrahedral intermediate that will pick up a proton from whatever you're given is the acid. Here again, it needs to be water. Water is more acidic than ethanol or any other aliphatic alcohol. And then we're all set up for our E1CB elimination of water. We'll take again our base at hand, which is hydroxide. We'll pull off again either of those 2 acidic protons that's also on the carbon next door to the one bearing the leaving group. So these protons, I would say, are alpha to the OH group because the carbons are next door to one another. And once again, if you'd rather put the, if you'd rather use the electrons in the carbon-hydrogen bond and put them in the carbon atom and use that resonance form, completely fine, 100% acceptable. Yet another one of those cases where if we were watching Chef John on YouTube of foodwishes.com, he would say, "You're the boss of your sauce." Or he would say, "You are the something something of your enolate," where he had the name of some famous person or thing, at least famous to someone in his age bracket. I often don't know who he's talking about. That would rhyme with enolate. But be that as it may, so you deprotonate this, you get your enolate. And the enolate will then, enolate of your enolate. That sounds like something he would almost say. Anyways, but whichever of the resonance forms of your enolate you use, you will then show the enolate collapsing. If necessary, if you use this resonance form of the enolate, you'll show the carbon-oxygen double bond reforming. You'll shift the electron pair, whether it's in the pi bond or on the carbanion in, to kick out hydroxide as the leaving group, and you'll get this species here. And again, there will be a tremendous driving force to lose water, and I'm confident that will happen quickly, even under the same reaction conditions. I don't think we could isolate this initial aldol adduct even if we wanted to. I think under the same reaction conditions, certainly if we so much as let it warm to room temperature, we will very rapidly lose water, because we're actually getting an extended conjugated pi system that goes all the way through from this benzene ring, through this carbon-carbon pi bond, to the carbonyl-carbon, which is also sp2 hybridized, going and extending all the way into the other benzene ring. So the only other question, and it's why I like to use something like this as an example, is how do I know to put the phenyl group over here as opposed to the methyl? In other words, why am I drawing the, let me see, the E isomer instead of the Z isomer? And I would predict that this would be more stable as opposed to the other stereoisomer with the methyl group being over here, merely because the benzene ring is bigger than the methyl group. And so in cases like that, I think you're on quite solid ground, anticipating that whatever is the most stable possibility for that new alkene that you just made, most stable in terms of substitution, most stable in terms especially of whether the E or Z isomer is more stable by according to a steric strain or something like that. But I feel quite confident postulating that this would be the major organic product, with the smaller methyl group near the rest of that molecule as opposed to the larger phenyl group. Good. Yeah, can't think of anything else. So hopefully you got something like that. Questions on that mechanism? And then we'll look at that mixed aldol example. We still have 7 minutes. I might even be able to let you out a little bit early, which I'm embarrassed to let classes out much more than 5 minutes early, but if it's 2 or 3 minutes, that's fine. I don't think you guys will be offended. Good. Well, actually, since I still have to draw the mechanism out, let's consider this reaction. This is what you would call a mixed aldol reaction, because your enolate is of a different species than the carbonyl compound you're adding to. So here we're treating this cyclopentanone derivative with sodium ethoxide and ethanol. Why sodium ethoxide and ethanol? I felt like it. That's the only reason. We could use whatever other base we liked. And now our electrophile is going to be benzophenone, which is diphenyl ketone. So it's 2 benzene rings with C double bond O in between. And the reason I picked that one is because benzophenone has no enolizable hydrogens. So there's no chance of getting a mixture. If we took 2 different molecules, both of which were enolizable, both of which had at least 1 alpha proton to the carbonyl, I would expect to get a horrible mess out of that. I'd expect to get, complex mixture of 3 or 4 or even more compounds out at the end. But something like this, I think, would react cleanly. In fact, if it were me, if I were doing this in real life, I would do what they call an inverse addition, meaning instead of adding the base to the carbonyl compound, I'd add the carbonyl compound to the base all at once. That way, every molecule of the enolizable carbonyl compound, which we'll get to that in a second, is immediately flooded with this large excess of base. So everything gets deprotonated cleanly, and you don't have to worry about forming any aldol products. In other words, that any given molecule of this dimethyl cyclopentanone is going to, at any given time, be much likelier to run into a molecule of our base than into a molecule, another molecule of itself. So we We deprotonate, we overwhelm this species with base, and we deprotonate it quickly and quantitatively. So let me make my ethoxide ion. And so once we've made this enolate, then we can add in the benzophenone. Or frankly, even if we didn't, even if we added both ketones at the same time, there's no danger. Because again, benzophenone can't enolize, so it's not going to react with the base, at least in principle. So the first step is going to be deprotonation, alpha to our carbonyl. We're used to this. We saw this happen a whole bunch of times in the last chapter, except now instead of adding, could have shown a little more restraint on that arrow, I think. Now instead of adding, let's say, a primary alkyl halide, we'll add in our other carbonyl compound. So what's our enolate going to look like? The other hydrogen is still there. I'm just removing it for simplicity's sake. So this proton is still there, of course. We'll have a minus charge in this oxygen. Let me put in also the lone pairs for clarity. And then we'll also have our nice juicy electrophile around, our benzophenone. And again, I hope you're all able to convince yourself that benzophenone has no enolizable hydrogens, because we have a benzene ring on either side of that carbonyl. And at that carbon-carbon bond, there are no carbon-hydrogen bonds. So we can't, so benzophenone has no enolate. So once that's in the reaction mixture with the enolate, whether or not we started that way, then very quickly our enolate will add to the benzophenone, and I would anticipate you'd get an oxyanion intermediate, looking a little something like this. So let's see. We'll have 2 benzene rings, 2 phenyl groups, and an O-. Looking very much like that. So next thing we need to do is put the proton back on the oxygen, look back at what I'm given. All I see is ethanol. So I've got to use that as my proton source, my acid. There is nothing else. Hopefully that writes it the right way. Good. I was a little scared it would go TE instead of ET. So there we go. And then once we get that initial adduct, this will now undergo an E1CB dehydration. There's still one acidic proton here. That's the one we'll pull off. And the reason we know it's acidic is because it's next to the carbonyl carbon. And so we will get, once again, an enolate. Our base is, yet again, going to be the ethoxide ion. So let's drop that in. Oh. Sorry, I was letting myself get, wait a minute, what's going on? Oh, let's see, had the wrong thing. Okay, so we'll make our ethoxide ion. And we're just 2 steps away from the product. We've got, oh, it already had a minus charge. Sorry, I'm allowing myself to get confused. We first need a minus charge, that'll be helpful. There we go. And so this is now going to pull off that proton. And maybe just for kicks, let me show you what that would look like if you drew the other resonance form. You drew the resonance form of the enolate that has the minus charge in carbon, which again, perfectly acceptable. Actually, wait a minute. Right. So we now have minus charge over here. So there's our carbanion. Also, that's just the other resonance form of the enolate. And that will now collapse, lose hydroxide as a leaving group, which again, ordinarily, you're not going to do. It's very rare you'll see hydroxide as a leaving group. It's a really bad leaving group. But in the case of these aldol dehydrations, it's good enough. And as I said, I don't think you'd even be able to isolate that beta hydroxy ketone, even if you wanted to. And that becomes clear when you look at the structure of the product, which is next. The next structure is that of the product. Why can't you use electrons from the hydrogen bond to immediately form the double bond and expel the OH? In other words, why do you have to make a carbanion? Why can't it be considered? Or another way of asking your question, which is a good one, is why do we have to say this is an E1CB reaction rather than an E2 reaction? And it might be E2 sometimes, but the way we know that the E1CB is likeliest is because we get an especially stable carbanion, because it's an enolate. In chapter 11, we said that in those cases where, actually we said 2 cases, where you get an especially stable carbanion, which this is because the minus charge is alpha to carbonyl, or if the leaving group is particularly bad, which it is here too, then that's going to favor the E1CB reaction. So yes, I think this is the best mechanism and the one that the majority of the molecules will take. I don't say every last one, but I think the majority. And so now again, look at this. Not only is this double bond conjugated to the carbonyl, it's also conjugated to both benzene rings. And hey, look at that. We don't even need to worry about stereochemistry. There's no E and Z possible here. But be that as it may, I think you would very quickly lose water here, and that it would happen majority by the E1CB mechanism. So with that, I'm actually out of time. I'm happy to answer any other questions, but I need to let you guys go.